In this question, we're given that a uniform cylinder of mass m and radius r is rolling down a slope of inclination theta. The cylinder rolls without slipping. You may take the acceleration due to gravity to be g. At what rate does the cylinder accelerate down the slope? So we are being asked to find acceleration, basically. So first of all, let's make a sketch. Suppose that's the slope, and that's our angle theta, and we're given this circle with radius r, and obviously, actually, let's move this up. Let's move this at the very top. Right, it's going to travel all the way down for a certain distance. So we can say that the total distance traveled in this particular case would be, so the total distance x would be r times an angle alpha, or let's just say beta. Okay, quite unusual, but it should be fine. So beta is the angle of rotation. So this is because the circumference of the circle is, we generally say r theta, where theta is in radians, but in this case theta is taken, so we would say r beta, and it would rotate a certain amount of times by a certain angle to cover this whole distance. We can now differentiate this to get, the distance, the derivative of the distance would be the velocity, which would be, so we would differentiate with respect to time, to give velocity times r beta dt. In this case, beta times dt, if we realize, is the same as omega, which is the angular velocity. If we differentiate again with respect to time, we get acceleration, which is a, and then we get ar omega dt. In this case, omega dt means change in angular acceleration. So omega dt we can write as, let's just say alpha, which is the angular acceleration. So we say alpha equals the radius times by alpha, so not alpha, sorry, a equals the radius times alpha, where alpha is the angular acceleration. Now, if we zoom into this and kind of consider the forces that act in this case, we would have, firstly, that's the center. If I take red color, we would have a force of friction upwards, so Fr. We would have a straight vertical down force of mg. We can also resolve this force in this way. That's 90, that's theta. This force, this component of the weight would be mg sine theta. And obviously this one would be mg cos theta. Then there would be another force acting towards the center from the point of contact, so which would be the normal reaction force, we would say. So this normal reaction force straight up there would be, so this would be r would be the same as mg cos theta, and the force of friction would be less than mg sine theta. Now, why is this happening? We know that it remains in equilibrium respective to the plane, right? So it's not going up or down. So the vertical forces have to equal to 0, which is why the normal reaction will be equal to this mg cos theta. However, we know that it's accelerating downwards, so the net force is downwards. That's why mg sine theta has to be greater than the force of friction. Then there would also be some sort of moment because of the mass of the cylinder. So we can say that the moment of inertia would be say in this case F. We need to find the moment of inertia because we would need to equate the moments. So in this case, the moment would be R times FR, where FR is the force of friction. Actually, let's make this in black. So the moments would be FR times by the radius, which I think in the question was small r, which would be equal to the moment of inertia, which let's say J times by the angular acceleration. So that would be alpha. Now, at this point, we can see there's some sort of similarity between these equations. So if we find alpha, we can if we find an equation for alpha, we can probably find an equation for the force of friction. So let's see. We can find J, so the moment of inertia for this particular cylinder. So let's just imagine the cylinder is something like this, from kind of the top, right? That's the center, and that's the axis of rotation. We know the moment of inertia, which we generally say I, is the sum of mi times ri squared. Right. In this case, in this particular case, we would have to take small rings around the cylinder. Small rings, so imagine just kind of toilet rolls kind of thing. So the net mass we're given in the question m, so total mass equals m, another s. We're given the total radius, so the maximum radius would be r, so the max radius, upper limit actually, so upper limit would be r, and lower limit would equal 0. Now this will be because we're going to integrate small bits and add them together. So assuming this cylinder has a constant density rho, we can say that for each individual ring, the moment of inertia would be the integral of from r to 0 of r squared dm. So dm is very small amount of mass. Now we don't know anything about any of these for now apart from the radius, so let's just say that's length L. Okay, so we can suppose the density of this cylinder is rho, so we can say that's m over v, where v is the volume, m is the mass, right? For small cases, for really small cases, so for example in the rings, this m would be really small, so the density would be dm over a really small amount of volume, so dv. Okay, now let's just imagine another cylinder, in this case more like a ring, right? And it goes to a certain amount of distance down and something like this. Okay, so this will be some sort of delta r, so like a really small radius, so that will be the thickness of this certain let's just say rho. So the outer radius would be something and the inner radius would be something. Okay, if we kind of open it up, if we open this whole thing up as say a cuboid, it would look something like this. I'm trying to make this look a bit 3D. So if I kind of cut this open from there, that goes down, that goes, well, let's just say that works. right? And that's obviously our length L, because that doesn't change. This is coming from a really small section of this big cylinder. This length is L, we're given. This length is, this length is the circumference of the circle, so 2 pi r. And this distance is dr, which is a really small change in the radius. So we can say that dv is the same as 2 pi r times by L times by dr. Okay, so now using this equation, we can say dm equals rho 2 pi r L dr. Now we can get our integral back. So bringing our integral, we have I equals the integral of r to 0, r squared, and then we sub in dm as all of this. So rho 2 pi r L dr. Out of these, we can see that density L and 2 pi are constant. So we can pull these out to get I equals 2 pi rho L integral of r to 0 r cubed dr. Now if we integrate this, we get I equals 2 pi rho L, and then the integral would be r to the 4 divided by 4 from r to 0. So pretty much just exactly the same. So pi rho L r to the 4 divided by 2. So I've cancelled these out by 2. Now if we look into this, if we kind of separate this out, so we get pi r squared L density times r squared. So I'm just going to separate these. Rho is mass over the volume, and the volume is, let me actually get a highlighter. So this volume is the same as this. So the density times by this certain pi r squared L, we pretty much get m r squared divided by 2. So that's the moment of inertia of this particular cylinder. Now we can finally actually use this value and kind of combine these two equations. My line just disappeared. Ooh, that's a weird line. So we can say FFR, which is let's just say FFR, because we don't know what it is. So FFR times the radius equals m r squared divided by 2 times alpha. So we get FR equals m r alpha over 2. Right, so we have the force of friction now. Now we can also consider what's actually happening with the acceleration. So another thing before moving on we can do is, from this equation we have alpha equals a divided by the radius. So I can sub in this alpha into there to give me FFR equals mr over 2 times by a over r, where a is the acceleration. So I get ma over 2. That's my force of friction. Now if we look into the actual motion of this object, we know that there's a force acting down towards the slope, so mg sine theta minus the force capital F FR equals ma, right, because it's moving downwards. So we can sub everything we know back in. Mg sine theta minus ma over 2 equals ma. All the a's cancel out, so we get g sine theta minus a over 2 equals A, and G sine theta equals 3A over 2, I think. Now we can just kind of get A on its own, which is not too hard. So 2G sine theta over 3. So this is the acceleration of the cylinder, and this is our final answer.